Next.
Hello.
Hello, Tyler. Nice seeing you. Nice seeing you connected. Okay. Just in case, you can consider immediately opening MATLAB, downloading the script from the email and run it. Otherwise, download it and run it, and I will give some comments. So I have also scrambled schedule today. I have another meeting at 12, so I'll try to squeeze stuff. And I will start next meeting right from here. It's fine if you can sit here, but there will be other people on the connection. It will be like university. Okay, so let me share the screen. And here are your subjects. That there is some admixture of your review in selecting one or another subject, right? So there are 3 teams: one for thermomagnetic, another for paramagnetic, and the third for anti-thermomagnetic. So the folks inside the team are very much encouraged. So while presenting and while writing your reports, you're very welcome to refer to materials that other parts of the team have made, because we are just practicing to picture bigger problem in smaller pieces, as well as you can make vertical connections and horizontal connections. So today I will show and explain what the experts or growing experts in magnetic susceptibility will conclude. So I will talk about the project for chem759 and the scripts that I have sent you by email and inviting you to run are for them. So basically, if we need to stop in 1 minute, just run the scripts, make the figures, and put them into the report. In the initial part, at the top of the code, please adjust the couplings. Current version, Tyler doesn't need to change anything. The code is the script is right with J. Payment should put it as small as possible, and maybe consult with Chris. I know from emails that she was exploring legitimate values of J. So Pius and Payman are encouraged to cooperate with Crystal and ask for the values. Crystal, please consider to be friendly to them and answer questions if they ask. So Humanity is encouraged to follow the trend. Should just put minus in front of J. So once again, this is the version of the codes that the names like version 12, version 14, and it is M or B, which is not mobilization as function for the field, and E or D, which is energy as function for the field, are designed for this last stroke. So if you are not among these 3 people, you may skip whatever we are doing right now, or you can do it fully closed, but for general educational purposes, make to see connections. I have downloaded this code and I'm running it here. So I put number of loop steps to 200. It will be done soon, and then I will go back discussing the code and its results. And while it is running, I'm doing freestyle speaking. So most of the time I will talk about this script, but briefly about the previous two books. So if you are trying to visualize microstates and plot density of states, so if you are Sophie, Christoph, and John, you may remember the density of states as this cone structure, like a palm with 33 fingers going up, 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 and then down, down, down. So those are basically number of microstates as function of energy, right? It's completed short return to it. So what do you do with coins? Just tell the right word. Flip. And when you just throw it and let it land, you just toss, flip. Oh. Okay. Okay. And what are just need to learn the right word. So what is the name for front and back parts of the coin, like overs and reverse? Head and tails, right? Do you have this head and tails coins in the first part of physical chemistry? Any problems, homeworks?
I don't remember any problem.
Okay, so we will complement it now. No homeworks, but you will do it in Sophie, Crystal, and John. I encourage to just maybe add a sentence or a paragraph about it in your work. So suppose, well, how many sites is in our model? Sophie, you were presenting this diamond structure. How many ruthenium atoms are in the model that you consider? Okay, and each of which has spin which can be up or down, right? Yeah. Now, suppose you have 32 pennies. 32 pennies, 32 coins. Okay. You put them in hands and throw them in the air. Then they land, and you count how many came with front, how many came with back, and put it in your notebook. Then you collect them, throw once again, and count once again. So the question is, what is the probability to have, for example, equal number of heads and tails? Or what is the probability to have only 2 heads? So nothing is not better, but I encourage all 3 of you. You can cooperate, you can choke this problem between you, but try to solve it and put it in your report. For each number of spins up, like 0 spins up, 1 spin up, 2 spins up, write down the probability. And if you didn't have it in first
Like
part,
in a table?
Yes, in table or in a graph, like a number of heads on the x-axis, probability on the y-axis. And this should come into this permutation equation, right? So I'll send this, well, it's just Wikipedia for permutations, so I'll send it to everyone. So this will make a connection between common sense and coins and this quantum problem of heat capacity and other properties of this correlated space. Make sense? Is it doable? Okay, then you can cooperate who will present what, so that if you, because each of you will present, but so that you complement each other rather than compete. Okay, I will go back. I will go soon to the scanning of magnetism, and just so that others do not feel bored. If you are in the second group, Chamberlain, I know Chamberlain is not in the class, but she will watch it in the recordings. Files and Ichi. So you are running the version of code that scans the temperature and finds internal energy as function of temperature, and you find response of temperature to the response of stored heat or derivative of energy over temperature, right? Capacity. So if we look in just simplest open sources like Wikipedia, here is an example how it may look like and how your results may look for J positive for antiferromagnetics. So it is the heat capacity computed as function of temperature for different values of magnetic field. And you see that if magnetic field is sufficiently large, there is a peak away from zero. Because as later, hopefully, Sohi, Crystal, and John will teach us, the magnetic field splits the peaks, right? Zero split. And then if magnetic field is large, no matter what is J, there is a ground state. And system behaves normally with a peak in stars large B has peak. As soon as we go to smaller and smaller magnetic field, and Tesla is really huge value. I think in the NMR facility on the department it is smaller than that. Crystal, can you say what is the maximal value of magnetic field in the equipment that we have at the department, either in Tesla or in Gauss?
It's 400 megahertz. So
No, megahertz is frequency. It's how it changes over time, but the static in Z direction that creates splitting.
I'm looking at that number.
Okay, you can tell it later, like in your writing or in presentation, but I think it will be even fraction of that. So like maybe 100 Gauss, 0.1 Tesla. So if it's more magnetic field, then the ground state becomes degeneracy and heat capacity gets maximum near zero temperature. So looking at this, it is an example how results that each is planning to do may look like. I do not guarantee that it will be exactly the same, but it is kind of a guideline. So you repeat computation of the heat capacity at a couple of values of magnetic field and see if it has maximum or it shifts one or another way. Make sense? Each please feel free to ask questions. Make sense? For bias, I think your dependence, your computer dependence of heat capacity on temperature should be sharper, and you also depend on magnetic field, but not as strong. And for channeling, it also it should be even sharper, but also never show the both bias and channeling are expected to obtain zero heat capacity and zero failure. And each is going to get this quite interesting and unusual behavior. So you are on the way to discover it. I'll share this link so in open sources Wikipedia to everyone right now. So spin liquids and permutations. Okay, now going to the code and analysis of data for Xinjiang, Payman, and Tyler. Tyler is here and Payman is not online, but hopefully he will watch the recordings. So the codes that are provided basically generate 4 additional figures that we never discussed in previous classes. So the code that I did run and hope you did run as well right now does not automatically scan temperature. Instead, it scans value of magnetic field. It's like one puts magnet closer and closer to center, or if it is electromagnet, one just tweaks the amount of current, so it becomes stronger or weaker. So one part is magnetization as function of magnetic field. It's like you can magnetize the domains in magnetic material. Right? Response, how this magnetization responds to the change of magnetic field. And then another thing which is more thermodynamic, how the field of energy depends on magnetic field, and how it, what is the derivative of energy in respect to magnetic field. So if magnetic field goes very large, then microscopic details will go away. It will just split linearly proportional, Zeeman splitting proportional to magnetic field, and energy will be linearly proportional to magnetic field. Just E equals minus B, nothing else with some proportionality coefficient. But if magnetic field is small, the dependence can be more different. So the code was starting to discuss it on previous meetings, but let me go over. So this line means nothing. P naught is just reference value. J is set up in this for antiferromagnetic, and we set up temperature here, but it will be reset maybe later. So let's scroll to the portion where loop is launched. I think I already went over it. Yes. Okay. So before, in previous versions of the code, some factors and temperature were multiplied by scan variable. So scan just goes from different numbers to set grid points. But now temperature or temperature times Bose constant thermal energy is fixed, but magnetic field is equal to this reference points times scan. So each time we come through the loop, magnetic field has new and new value, and the rest of the code is the same. The only thing that we have a continuous dependence on magnetic field, and later on we do derivative on magnetic field. So there are some minimalistic changes in relabeling the figures. To the very end, like what we called x before x under variable x before it was temperature. In this version, it is magnetic field, and then one plots like y is energy and z is magnetization, and one puts labels there. So basically, right now, since time is up, the semester is finishing quicker. Those who need to run this code, you just modify the value of temperature, rerun and store figures, and then just put them in the report and analyze them. So what comes up after the code is running? So this value of density of states corresponds to a very large value of magnetic field. It's much bigger than before. It spans over several electron volts. It's just an example of, so it's the same shape, but it is strongly, the degeneracy is limited. Now we do have magnetization as function of magnetic field in several ways, and when magnetic field is huge in then all spins are oriented towards magnetic field, and it is maximal number of spins down minus 16. If the magnetic field is 0, then magnetization is 0 for antiferromagnetism because it is energetically favorable to have them antiparallel. Right? And in between, there is some rate of change. So at lower value of B, there are spin-spin interaction in thermal effect. At larger value of B, there is only magnetic field. And if one takes derivative of this curve, then when the slope is maximal, when it goes down, there is this peak or anti-peak. So this the derivative of magnetization over magnetic field is called with this word that is hard to pronounce, susceptibility. And for different values of J for different materials, ferromagnetics, paramagnetics, and antiferromagnetics, it will have quite different shapes. For the right side, at large magnetic fields, it should just decay linearly, and the position of this peak will depend on the parameter. So you may try to make these figures at different values of temperature and just share your observations. So, any questions about this part? And Young and Tyler. Tyler, do you have any questions?
Not at this time.
Okay, were you able to generate figure like this? Tyler?
Say again?
Were you able to run the code and generate figure like the one is shown on the screen?
Yeah, I ran both set of codes.
Did you get it yourself on your in HumanLab?
Yes.
Were you trying to change temperature and get this figure once again for this different value of temperature?
I have not changed temperature really much because I'm not sure of the fact of what exactly I'm supposed to change.
Okay, let me show it right now. Okay, so line 107, right now temperature is 900, and then there are conversion factors into atomic units. So if you want to put room temperature, just change it to 300. And you can try different values with understanding that the smaller the temperature, the uglier the figure will be. So if you put like 1,500, it will be really smooth and nice curve. If you put smaller and smaller temperature, it will look ugly. And then I will start the code once again, and you please do the same. Okay? Tyler?
Okay.
Okay. Xinyan? Yeah. And for your version, please consider to change the J, like put minus sign here, and then try the same experiment. Okay? Okay. So there is another version of code that looks for the energy, and if I will run another one, if you go over the time that we have now, it runs for about 20 minutes, but I just pre-made the figure that you already saw. And if one scans magnetic field and looks for energy, so it goes down as magnetic field increases. and the slope changes. So when slope changes means the interaction with magnetic field becomes dominant, and before there is interplay between the skin coupling and temperature. And if one takes derivative of the magnetic field over derivative of energy over magnetic field, then in the high magnetic field value it will be constant because the slope is constant. And here there are some non-trivial things, and interestingly that it's not smooth. There is some error and values change sign. So just if you have steam and energy, you can generate figures like this at different temperatures and put them into your coordinates. Okay.
Our magnet's 9.4 Tesla.
How much?
9.4 Tesla.
9 point. Okay. Okay. Yeah. Thank you. So it is doable in the lab, and it is within the range that we see. This one here. So it is in between. So it is doable. We can put sample of this material into the device at the department if needed. Okay. So I'm open to any questions, especially from Xinyan and Tyler, and Payman if he joins. Also, let's check if there are any additional questions from other teams. Yes. Huh?
I have a question.
Yes, please. Yes. I will not be able to bring the camera, but. So keep J the same, and you try to use DBT.
Yeah. And one action should have one. And it's kind of weird that
Mhm. So right now, just report what you observe, and maybe send it to you and try to see what is going on. Looks like here the units enough temperature. It's expected that it will go up and then go down. So the range of temperatures is insufficient. Okay, let's go to the script. It's good. Let's if there are additional technical questions, prefer them after the museum or try to answer as much as possible.
I think the value. So the Y value here, for how many?
Even nice seeing you connected. We will be not as long today, but everything we did is recorded. And there are some messages in the recorded stuff specifically for you. If you just joined and do not know what to do, just try to download the code version 14 from the email and run it on laptop. So expand the range of the commodities. And now it should go, it should be sufficient distance to go up. And then, and the main word, it's another
Sometimes the one speed range.
So we'll come close to the way it comes down. We should be treated like questions. Any quick questions? Two of the first. Okay. If you set the order, when kids play the sports, they break them. So we do a lot very well. And just the personal little experience with this stuff. If you literally put zero, you will probably give some unstable results. So just put this a little smaller value. Also, it's check what she was exploring this. She was summarizing it as a lot of people. As kind of important, it's very good. So, which do you remember which subject you studied? You know, okay. Then energy assumption, temperature, and heat capacity assumption. Okay. So chat usage, she understands. It's temperature, it computes and force energy, which is Depends for the school. Depends on development. Yes. And also do for some of the roads are to be expected from other. And expect to solve keep I'm not explaining this different level. And just say images and place them in the so collect from the slides and then you will select and after it counts the 200 it will generate figures just on the it's fine. So yeah. Yeah, I'm running. So here, number of steps is 200. So A will the one step. So it will stop when you reach 200. So you need to and you have much yeah. After it compare checks. So you're studying. Don't change it now. Let it finish, and then we get home. Change J to negative. Run once again and for the figures. There will be two figures from this one and two figures from this one. Yes. And then put them into PowerPoint. Yes, and then repeat it with another temperature. But feel free after you generate it just once, send the results to me and we discuss. Okay. Yeah. Thank you. Okay. So I apologize. I need to connect another meeting right here, but you can keep sitting and using the equipment. Right. Okay. Okay, here are results for room temperature, and you see that the figure became sharper, right? But this sharper figure has a little bit uglier, so the noise is bigger, and it's more difficult to analyze. But it is a critical temperature phase transition. Right? Okay, Crystal, Payman, Tyler, I'm going to disconnect now. Please send questions by email, and I will be looking and maybe set one-to-one meetings as needed.
Okay.
Okay. Yep. Thank you for
Sounds good.
dedication to the class and for understanding. Just have a meeting starting in half a minute. Okay. Class is ended. You're welcome to sit in and use equipment.